Have you ever been to a science museum, placed your hands on the electrically charged orb, and wondered why your hair is standing upright? Or wonder how we are able to calculate the mass of objects so thin, such as a piece of paper? Why doesn't a dam simply burst from the pressure of the water? Well, in fact, they are all defined in terms of surface integrals.
Let's begin with the equation for the surface integral. In a surface integral, we're integrating the vector g of r dot ds, where ds is the vectorial surface element that equals to the unit vector n dot ds. The dot here refers to the dot product, which can be interpreted as the projection of one vector onto another, thus giving a number as the result. If we take the vectors a and b into their components, then the dot product of the two vectors is defined as simply multiplying the corresponding components. To demonstrate, if we assign vector a with the values 1, -3, 2, and vector b with the values -2, -1, and 2, putting those into the formula, a dot b then gives a result of 5, which is a scalar. Now let's take the surface of a sphere, selecting a piece and magnify it. Here we have again the vectorial surface element ds. It is perpendicular to the surface and the unit vector n shows the direction. The important step when integrating over a surface is to parameterize the surface. After some manipulation, the surface area element ds is replaced by this equation of del r over del x cross del r over del y times dx dy altogether. Here we've used the cross product, and its definition is as follows. For vectors a equals 3, -3, 1, and b equals -4, 1, and 1, if we plug the numbers into the formula, the cross product would be -4 in x, -7 in y, and -9 in z, which unlike the dot product, gives the vector.
One of the key uses of surface integrals is to calculate electric flux through a surface using Gauss's law. Electric flux, denoted by phi, is the total number of electric field lines penetrating a surface. So for an even surface, Gauss's law is quite simply phi equals E into n hat into A, where E is the electric field enclosed by the surface, A the total area, and n hat the perpendicular element of the surface. But what about for an uneven surface? Well, this is where surface integrals are useful. Since the perpendicular vector changes depending on the orientation of the surface, n hat changes, causing the component of E, normal to the surface, to change as well. Thus, we divide the surface into little sections and label those dA. Now we use Gauss's law. Since dA is the area of those small divisions, the equation becomes this. Defining d vector A as n hat dA and then integrating through the surface will give us the equation for flux, which can then be used to find the charge enclosed by the surface. Gauss's law essentially is just summing the flux through the small areas, dA. This is in essence how surface integrals work, adding small components of the area together to form one entire surface.
Here's an example problem. Here we are being asked to integrate the function g of r over a surface, which is given by z equals x squared plus y. The limits of integration are 0 to 1 for both x and y. First off, we need to parameterize the surface by constructing the r vector that the function g will be acting upon. This is the usual x, y, z format, except instead of z, we have x squared plus y. We now insert this function into the g function. The x component of g of r is z, which we know is defined as x squared plus y from our parameterization, so we write x squared plus y. The y component is 0, and the z component is x. Now before we integrate, we must remember that our surface element ds is given by del r by del x cross del r by del y dx dy. You'll have noticed we use del x rather than dx. This indicates partial differentiation. It's similar to implicit differentiation, except you treat the other variables as constants. Now performing the cross product, we get our final ds. Remembering the formula for cross product, now we have our surface element as it's finally time to integrate. We take the dot product of our two vectors and integrate the result, remembering our integration limits, where the dot product is given by firstly integrating with respect to y and substituting our y limits, and then integrating with respect to x, not forgetting our limits. And we find that the value of this surface integral is -1/2.
So remember, next time you wonder about a surface charge, the mass of a thin object, or the pressure force, these are all physical applications of surface integrals.